And tonight, here we go. We have Elaine Short. And Elaine, I will turn it over to you.
Great. My glasses have gotten a little bigger since that picture. All right, let me get my screen share up. All right, and I do have the grid view up, so if you happen to have your video on so that I can tell whether or not you're laughing at my jokes, I definitely appreciate that. It helps me make sure that everything is landing as it should. Yeah, so I am Elaine Short. I am an assistant professor at Tufts University. I work in human-robot interaction, which you all in the human-computer interaction community can probably infer what that might be. It is the intersection in a lot of ways of human-computer interaction and robotics. And I'm particularly interested in assistive robots, where I define assistive in a very broad way, which I'll talk a little bit more about later. I run the Assistive Agent Behavior and Learning Lab, which if you spell that out, you will notice that that is the ABLE lab. I spent probably more time picking out the acronym for my lab than I did deciding what university to work at, because you're definitely stuck with your lab name for the rest of your life. So I was very pleased with this one. All right, so what is my main driving, motivating question in all of the research that I do? And if I get selected on the right window, I will tell you about it. All right, so I care about robots helping people. So that means I think about human-robot interaction. I think about assistive and service robotics. I lump these together. So the difference between them, if you meet someone who isn't me, is that assistive robotics typically refers to robots that are designed to help people with disabilities. And service robotics typically refers to robots that are designed to help people who are presumed non-disabled. And I have a lot of problems with dividing up the world that way, but we'll just say robots helping people sort of in that area. And then I'm also very interested in robot learning for a lot of reasons. One, from a technical perspective, as a computer scientist, I think machine learning is cool and interesting. But also, I think it's one of the best tools we have for understanding what people want. You can go out and you can pre-program a robot to complete some task. If you know what the task is in advance, we can just design a custom controller that'll do that thing. But if I need to put a robot out into the world and I need it to be able to do things for people, I can't anticipate in advance everything that a person might want. So learning is a really useful tool to be able to figure that out and model what people are looking for. And so the, I don't know, maybe more fancy statement of purpose is that I am interested in building autonomous robots that serve user needs in social environments at human-friendly timescales. And hopefully you will see each of the pieces of that show up in different parts of this talk. So autonomous robots, I am a computer scientist by training. All my degrees are in computer science. So I care about robot intelligence. I tend not to do a lot of robot building. Every roboticist at some point in their life has to build a robot just because they break, it's a new technology. The robot that you want doesn't exist, and so you have to build one. But at the end of the day, I'm interested in programming the robots. Serving user needs, right? I think about human-centered design, human-centered computing, sort of just a human-centered sort of philosophy on life, which I will not have to sell to this audience. Sometimes in the robotics audiences needs a little bit more convincing that like, oh, people are important and thinking about humans matter. And when we talk about social environments and human-friendly timescales, I'm really talking about robots that actually work out in the world. You'll see when I talk about my more recent work that there hasn't been a whole lot of robots out in the world recently. That is because the last, 2 years have maybe not been the greatest time for humans, robots, or interaction. So trying to do all three at once has been a little challenging. But in general, I'm always trying to get robots out of the lab into the world, into human environments, and doing things that are actually useful. All right. So what do I think are the kind of core problems when we're doing this? Well, if you think about HRI in the lab, I think of it as kind of like this, old-fashioned dance. So I have this nice drawing here, and I know one of these is Lady Jersey. I don't know who these other folks are. They're probably terrible people. But we have this old-fashioned dance. There are steps, there's rules, it's formal. Everything proceeds at a certain pace in a certain way. And so you have a lot of external structure, and that external structure is being imposed by what environment you're in. There are rules that you have to follow. In fact, there are lots of rules. Who can approach whom at what time? What order do things proceed in? There are steps to the dance that everyone follows. Everybody knows all of these rules. Participation is exclusive. And here, I don't necessarily mean when we talk about HRI in labs that we're like, oh, you have to be at a certain level of the aristocracy to come to the lab. But what I mean is most HRI labs are on campuses. Being on a college campus is a certain kind of privilege. Who we are able to recruit, who can take time off to participate in studies, all of that is relatively exclusive. And last, and in some ways most important, everything is relatively slow paced. I am aware that there are old-fashioned dances that are also fast, but in general, things are moving a little bit more slow paced, a little bit more stately. And this is really how HRI works in the lab. You bring someone in, you give them instructions about what they're supposed to do. They know that you, the experimenter, are there watching them. Again, in this audience, maybe I don't need to explain too much about experimenter effects, but if you know that somebody who is at least metaphorically wearing their white scientist coat and watching you, then you might behave a little bit differently than if you think you're completely alone. Similarly, we tell people don't touch the robot in that way, don't mess with the robot. All of these things, we actually give these rules. We recruit primarily from our campuses. And again, the pace, we often enforce turn taking between the human and the robot, which means the human has to wait for the robot. Now, sorry, I've got a weird noise here. Okay, well, hopefully it'll go away. HRI in the real world, on the other hand, is more like this. It's like a mosh pit. Actually, this is a free Creative Commons licensed image for mosh pit. And no, this mosh pit doesn't have a particular, it's like a small group of people, and you notice the background's really empty. If you're not familiar with a mosh pit, which sometimes when I give talks, people are not familiar with mosh pits, it is basically at a concert, particularly a hip rock and roll concert. There will be an area close to the stage where everyone is dancing really close together, often jumping up and down, and everyone's really packed in, and it tends to be pretty wild. And so HRI in the real world, right, it's chaotic. Things are happening at all times. It's not, oh, it's so quiet except for the thing that's important. There's a lot of stuff going on. It is a little bit more democratic. I never want to claim that this is fully democratic. We don't always put our robots out that much further from the lab. Even if we put robots in, public spaces, they're typically indoors. They're a little bit monitored because we don't want the robot to find its way into the back of someone's car. But it is a little bit more democratic. We're not controlling quite so much who is interacting with the robots. It's also noisy. And by noisy, I don't mean, I do mean in the sense that there is a lot more sound. But I also mean in the sort of computational information sense that there's a lot more noise. There's, numbers vary more. Any sensor you have, everything is noisy. I just had a talk with a student today where they were saying, oh, well, I'm going to simulate it. And I said, oh, in your simulation, are you going to assume you exactly know where every object is in the environment? And they were like, oh, yeah. And I was like, yeah, no, you can't assume that. And so that's what HRI is like in the real world. You often don't know where things are. You don't know where people are. You don't know what's happening. It's all very confusing. It's also super fast paced, right? Much like people jumping up and down, people are going to do what they're going to do. And especially if you're in a situation where people don't need the robot, they will move at their own pace. I'm interested in things like robots in groups, where if you have two people in an interaction, they will interact with each other at the pace of human interaction, and they will interact with the robot sometimes, if ever. And last, and probably the most important, assumptions fail when you move from the lab into the real world. Again, I probably do, there's a little bit preaching to the choir on this, because most HCI folks have some experience with humans and the human things that they do. But this certainly is equally true of robots. I usually tell people to think of robotics as everything that can go wrong with your computer combined with everything that can go wrong with your car. So to give you kind of the sense of the number of different things that are happening and the different ways that they can fail. Now in my research, so I said I like HRI in the real world. I do HRI in the lab. It's a great place to start. There's lots of interesting questions we can ask there, but I mostly care about this HRI in these more wild environments. And so we take these algorithms. A lot of HRI research, especially algorithmic HRI, is developed in the lab. It's like Lady Jersey here. And what we like to do is we take these algorithms and we actually try and modify them so that they can work in this new environment, like giving Lady Jersey here her cool crop top and sunglasses, so that she can now be in the mosh pit with everybody else. All right, so that's the general philosophy. I'm going to walk through some areas that I've been interested in over the last, whatever, 10 or 12 years that I've been working at HRI. And then I will talk about a couple specific projects, and then we'll talk about some of the more recent work that's happening in my lab. All right, look, this animation bears looking at one more time. I love Lady Jersey and her deal with it sunglasses. All right, so my PhD was in socially assistive robotics. So this is one kind of getting robots out into the world. Socially assistive robotics is a field that looks at robots assisting people through hands-off social interaction. So this is socially assistive in contrast to physically assistive robotics. And I've been involved with a bunch of projects here, including post-stroke rehabilitation, which I realize the robot is actually being covered up a little bit. The robot's name is Bandit. You can probably see enough of it right now. And then a bunch of work with small, cute robots. You can see my little fluffy friend. That's Chili the dragon, who we used with robots, used with teaching nutrition in schools to kids. We used a variation, actually a slightly different skin for the robot, with multi-generational family groups, looking at kids, grandparents, and parent generation. I think actually this picture is a great uncle and a kid, or it's a grandfather and uncle and a kid, something like that. There's an uncle relationship in there. And also looking at how robots can actually moderate group interactions. So what happens when you put a robot into a group and try and use the robot to make that group function better. More recently, I've been interested in social environments more generally. So this is thinking about HRI in the context of human-human environment, human-human and human environment interaction. By which I really mostly just mean getting robots out of the lab and into spaces where there are people. We often, even when we think about robots out of the lab, we talk about field robotics. People are usually picturing you're taking a robot out to a literal field somewhere and driving it around, taking a drone or an outdoor robot. But I'm interested in robots that are in spaces that people are in, because I'm interested in people, I'm interested in human robot interaction. And it can actually make the human robot interaction different if you have to do it in the context of other people and in the context of people interacting with the environment or moving through the environment who may or may not be interested in the robot. So one interesting thing from our study of robots in public spaces, which I actually will talk about in a little bit more detail, is that people very rarely come up to the robot alone. It's typically when people come up to a robot, at least at this point in time, it's in a group of people because there's one person who comes up to interact with the robot and 3 people behind them going, oh, go do it, go talk to the robot. You do it. No, not me, you do it. And so that kind of interaction and understanding those dynamics can be really important for the robot. I already talked a little bit about the group moderation. Some interesting results there that I won't have time to talk about even if people aren't paying attention to the robot, what the robot does in a group matters and can make a difference. We see that in my work and also in some of the work from the other people in HRI who do research with groups, that even when people are talking to each other and not focusing on the robot, what the robot does can change people's feelings about the group, can change how well the interaction works. And then finally, thinking about attention and interaction is sort of a first step, right? The first question you might ask when you're in a group and trying to interact with, or when you're in a public space and trying to interact with someone is, are they paying attention to me? So if you've ever had to give out flyers or sit at a table and try and convince people to join your club, you may have some experience with this of like trying to make eye contact with people, see if they're paying attention to you. Sometimes you can tell they're paying attention to you, but they don't want to interact with you. And having robots be able to actually understand and model that and pick who wants to interact with the robot, who's paying attention to the robot, who doesn't want to interact with the robot. That all is an area of interest for me and something that I will should have time to talk about in more detail. Actually, I think it's going to be the first thing I talk about. Okay, so I do have some videos just so you can at least see some robots doing stuff. I like this video of the robot and this person working together because you can really see how much faster the person is than the robot when we don't constrain them to take turns. And certainly if you're ever seeing another HRI speaker, please don't ask them mean questions, but you can look and you can think like, did they force the human and the robot to take turns or not? Sometimes we even design our activities or design our experiments so that the robot and the person have to take turns. And in this experiment, Mai Lee, the grad student that I did this paper with, actually specifically designed this interaction so that they don't have to take turns, and was looking at how you make a robot that's a good teammate in that context. And I mentioned I'm interested in machine learning. It's only kind of because everybody's interested in machine learning. But like I said, it's a really great way to come to understand what people want from a robot, how to get robots to do things. And so a lot of work I've been doing recently has been in interactive machine learning, or learning from humans, learning from demonstration. And we can think about when you have a person actively in the loop with a robot. Robots are slow, humans are slow. Together, well, humans are faster than robots, but still slow. And together, you end up in the situation where you can't assume that you have infinite data, which often very much pains the people who do deep learning, especially if they want to learn from pixels. The fact that I might say, oh yeah, I'll give you 25 data points. All right, now learn something for me. That's, maybe you have to completely change your approach around, or you can use some of these techniques where you leverage what the person is doing to try and learn faster. whether that's things like trying to use corrections, let a person correct what you're doing, using information about their behavior, in this case, gaze, to understand what's important in the scene. We learn with realistic attention from users, so taking into account, all right, person can teach me things, can help me learn faster, but humans don't have infinite attention and they're not perfect. They don't always give accurate information. How do we handle that? And finally, we can do things like use simulation to try and reduce how much data we even need in the first place. Although I will say I tend to be more interested in the interactive stuff with humans, again, interested in humans, than in the purely sim to real or real to sim kinds of problems. All right, so that's an overview. And so I want to talk in a little bit more detail about two projects that I mentioned briefly. These are both projects to do with robots in public spaces. This is work that I did during my postdoc with Andrea Tomas, but it actually lays the groundwork for some of the work that my students have been doing more recently. So I'm going to talk about these different projects, and then we'll talk a little bit about more recent work. So if I want to build a robot that can help people, one of the first questions you might want to ask is, how does a robot know that it's time to help someone? How does the robot know that a person wants the robot there? And so something that I've been thinking about in the context of public space robots is this idea of contingency. And what we mean by contingency here is the idea that when the robot does something, a person does something, and the thing that the person does depends on what the robot's doing. And in practice, in something like this atrium, that might look something like the robot says hi, and if the person says hi back, this is Miley, my co-author on this paper, I should add, then we want the robot to, well, in this case, the robot's asking for help, but the robot might offer to help, the robot might give information, or it might try and give the person a flyer. I don't know, get the person to sign up for robotics club, whatever we want to do. On the other hand, if the robot says hi and the person doesn't respond, maybe we don't want the robot to keep talking. That'll get pretty annoying and a little invasive quickly. And another thing that we want to think about is doing this across environments. So we looked at two different environments in this work. One is the robotics lab. And actually in this study, I told these grad students that they had to be in the lab and they had to work somewhere where the robot could see them. And you can see me in the picture as well. And so you can see it's a lot quieter. So I talked about HRI in the lab. It's a lot quieter. There is that big glass window in the back, and you can see a few people going through the hallway. When you compare it to the atrium space, you can really start to see the difference. I mean, in particular, this time lapse actually covers a class change. And so you'll see it's quiet for a little while, and then all of a sudden there will be like bunches of people. So it's actually not just noisy, but it's noisy how much noise there is. So you get these like big changes over time, changes in how much changes are happening. This atrium was also a lot of fun. If anyone has done anything with computer vision in the room, the atrium was a lot of fun because it was skylights up top, which meant that you had the light changing at every hour of the day, which makes all problems more difficult. So there is some prior work in this area looking at who's engaged or who can be interrupted. But in this work, we're going to not care so much which person is responding, just that someone is. In some sense, the robot doesn't actually need to know who's talking to it, which sounds a little wild. But if you think about it, the question we're trying to answer is, should the robot keep going with what it's doing? And if it gets it a little wrong, like, oh, I thought it was you, but it was the person next to you, that's actually kind of okay, because it can just keep going, keep doing what it's doing. There's also work that uses contingency as a tool for learning and reasoning about the world. This is actually complementary to our approach. Our approach is going to tell us about when a change is unusual, not just when something is causing something else. Also, some of my more recent work actually builds on some of the contingency work that is looking at learning about the world, reasoning about causality. Other approaches from the lab that I was in were either not real time, there's a graph-based approach, or a lower accuracy using a support vector machine. But this approach will show is both very fast and pretty accurate. So what are we doing with contingency here? So we define contingency in this work as a change in the environment after a critical point in time. And that critical point is going to be when the robot does something. So we're going to ask, when the robot does something, does the environment change? And does it change in a way that's unusual? And we're basically going to do this with standard statistics, which is really nice because they are very fast to calculate. In fact, the standard deviation you can calculate online if you want. You can run into numerical stability issues. So in practice, we didn't, but you can calculate it online. It's super, super fast. And it doesn't require a ton of data to train, which is going to be good. As we'll show later, we get pretty good accuracy using a total of 26 data points. And what we're going to look at is so the HCI people in the room should recognize this is very much inspired by your standard statistical testing. We're going to look at the variance before anything happens, the variance afterwards, and the overall variance, the combined variance of the two. And we're going to look at this over time, because what we want to do is we want to catch when we do something and there's been a big change occurs. In practice, for a lot of the features that I was looking at, this change might actually be like multiple orders of magnitude different. So we write that all up. This is what it looks like. It's called, again, you'll notice a theme of acronyms, beautiful acronyms, very popular in robotics, I guess in all of computer science. This is CIRCLE, contingency for interactive real-time classification of engagement. It also has this nice, cyclical metaphor to it. So we're going to calculate a change metric, and this is the ratio, the maximum of the ratio of the variance before the robot probe to the joint variance, and the variance after the robot probe to the joint variance. So this is going to catch changes in variance, increases or decreases in variance of the signal. It's going to detect increases in the mean. It's going to detect decreases in the mean. Basically, it can tell if someone's talking and then stops, or isn't talking and then starts. It can also detect someone's moving and they stop, moving, they start, they move one direction, they move a different direction. So we can detect lots of different kinds of things here. We're just looking for changes. We calculate the mean and variance of the history. We use a trimmed mean and a trimmed variance because we are specifically looking for outliers here. So we don't want outliers incorporated in our mean and variance. We want to get rid of them because that's what we're looking for. Robot does its thing. We're going to wait. And then we're going to just count how many features of the ones we were looking at had a big enough change that we care about it. And you'll notice there's some parameters here, which I'll talk about in a minute, that we need to set with data. And then we're just looking if enough. And what's really nice about this, of course, is compared to this prior graph-based approach, it really doesn't take any more time to calculate this as you add higher dimensional features. We don't have this like exponential looking curve. It's just pretty flat. Very fast to calculate. So I mentioned parameters. We have how long of a window we're going to look at. We have how much of a threshold we consider to be a large change. We look at how much history we should compare against. And then, of course, the number of features that we want to have changed in order to count something as being interesting. And obviously, how many features have changed that we care about is going to depend on how many features we have overall and what those features are. So you might set it so that you have to have a change in visual and audio features, or maybe you only care about one, or maybe you care about all of them. It just sort of depends on what kinds of changes you want to look for. So because we have all these parameters, we have to collect some data, and we're going to collect 3 kinds of data. The first 2 are both acted. And when I say acted, the actors, grad students from the lab, were given instructions of something to do and then told to either react or not react to the robot. We didn't tell them how to react. We just said react or not. And the ongoing activities were things like walk in front of the robot, stand in front of the robot and play on your phone. It was very popular. Grad students getting to do research while also looking at their phones. I think we might have also had like 2 grad students talking to each other and then react to the robot or not. And we did this both in the lab and in the field. We then collected natural data in the field by having the robot actually do these probe behaviors and then having someone live annotate whether or not the robot received a response. And the actual interaction in the field was the robot asking people to fill out a survey about robots. In practice, we had a very low success rate of people actually filling out the survey. And so we're not going to look at the survey data, and we don't have to worry about some of the effects that happen when you have a robot asking questions about itself. We're not going to worry about that. The important thing is, did people respond or not? We're very inspired by this problem of trying to get people to sign up for your club or trying to hand out flyers in a public space. We had live annotation by a coder. This basically was so that we didn't have to record video. You'll also notice I have some videos in here shortly. You'll notice in all of the videos, it's acted. They're acted. It's me. And that's just because basically for privacy of our participants, we didn't want to record them in this public space. So we just use acted data and we use live annotation, so we're not recording any video. And then the outcomes we were looking at were the number of times the robot made a request, the number of responses it received, how accurate it was, and then a metric that I personally would like to see adopted throughout HRI studies. I've actually seen it in a couple other studies, which I call the selfie metric, which is how many pictures people take of the robot, which is a rough estimate of how engaging or how interesting is the robot being. People love to take pictures of the robot. They also love messing with the robots, but that maybe I'll have time later to tell stories about that. So we did some feature selection. In the interest of time, I'm not going to go into a lot of detail on this, except that if you are doing robotics in public spaces, I highly recommend the sparse optical flow is awesome for trying to detect things about crowds, about people in crowds. Somehow it was just like really super excellent feature. We also looked at some audio features that are correlated with speech. So amplitude's the obvious one, but also energy in different frequency bands, and the spectral flatness, which is just a measure of how much a sound is like a tone versus how much it's like white noise. And that can also, speech occupies a certain part of that range. This was also helpful because at the time we were doing this research, the building was still under construction. And so there was a lot of loud beeping noises from construction equipment. So here's what the robot behavior looks like. And like I said, I acted this with my small glasses.
Hello.
Hi, Polly.
Would you mind doing a survey for me? You can complete the survey using the laptop on the table.
So once again, you see robot is slow, and you can hear the options of what it has to say. It has this longer thing that it goes into if it receives a response. And then here's the robot again, but this time I'm gonna do actually like a little like swishy dance in response to the robot instead of waving. because I wanted to show off that we're really trying to detect any kind of response.
Below.
Get used to the environment. So, but if I like,
Would you mind doing a survey for me? You can complete the survey using the laptop on the table.
And you can see once again, the robot is accurately detecting that I was responding to it. In this case, I'm attempting to respond to it. Now, this is probably my favorite slide about this work because it really shows why we care about doing this looking for contingency and not just doing a classifier. So here we have a contingent response. You can see the different features. If the dot jumps, so the bar is the average. If the dot jumps above the bar, then that means it's actually, I guess not the average, but the threshold. And if the dot is above the bar, then it's enough that we care about it. It counts as a change. If the dot's below the bar, then it doesn't count as a change. You can see here I'm waving, and this is, I think, me again waving and saying hi, Polly. But the non-contingent one, I love this example because if you were just doing a feature-based approach, a rule-based approach, or even maybe trying to train a classifier, this would be a problem because you would say people who want to interact with the robot, if they're standing near the robot, facing it, looking at it, and talking, probably they want to interact with the robot. But in fact, what's happening is this is another student from the lab, Adam Olivato, talking to Mitch Pryor, who's his co-advisor, and he's explaining what we're doing in this experiment, and he completely ignores the robot's probe. So they're doing all the things that you would expect to see from someone interacting with the robot, but because they don't respond, the robot correctly classifies this as non-contingent, that they're not responding to it. So this, I think, is a really great example. And this happens a lot to robots, right? Especially if they're not very responsive to a person or they've been doing the same thing for an hour. People will come up and talk about the robot to each other and just not respond to the robot when it does something. So accuracy was pretty good. So this is on accuracy on our data sets. So 90% in lab, and you can see a drop when we go to the field, which is what we would expect, but actually similar and even slightly better accuracy for natural data. I think most people kind of talk back to the robot, and that makes it easier to detect, whereas some of the grad students are like, maybe they're on their phone and they just look up at the robot, which is a little bit harder to detect as a change. We also went out and ran this live in the atrium again, and we got fewer requests, and more or less equal number of responses and more photos. So I'm really hoping this photo metric catches on. Accuracy was similar with the accuracy in our previously collected data, so we don't see a huge drop here, which is very comforting. And using field trained data using acted field data on natural field data worked not great, but it worked at all. And trying to transfer between the lab and the field basically doesn't work, which is not that surprising, but again, validating the importance of going into the field and actually testing things and designing things in the space that you want them to run in. So we have this algorithm. It lets the robot quickly detect these contingent responses and not make assumptions about what those responses will be. If the person waves, great. If the person bows, great. If the person does a backflip, great. We can still detect that. And currently, we're thinking now about what other kinds of signal processing, signal-based models can be used to actually detect contingency and therefore, hopefully, attention. So my student, James Staley, has been working on this problem of detecting attention and interaction. I already talked about the different methods that have been used previously, but he's working on developing a more mathematically sophisticated understanding of what contingency looks like based on information transfer and actually using information theoretic measures. So he is actually using a measure called transfer entropy. So given the entropy, we can look at mutual information. So mutual information is essentially how well can you predict a signal? How much better can you predict one signal given a second signal? And so you can see in this Venn diagram here, you can sort of see it's the overlap of the two. It's how much benefit you get from the second signal. We can then think about, all right, so these are all probabilities, so we can condition them. So we can look at conditional mutual information. Given a third signal, how much benefit do we get from a second signal? And we can use that to actually condition on the past behavior of the person and the past behavior of the robot. And the question is, how much more predictable is the behavior of the person given the past behavior of the robot? Which helps us bring temporal structure back into the problem that if you just use mutual information, you actually lose. So James has run a preliminary study. This is a 1D example. So remember I said people were going to go away for a little bit. So this is done in the last 2 years. And so people are, human interaction with robots is a little bit out of the picture, but we have a 1D example using little arrows. The leader can rotate to any value at each time step, and the follower can either move instantaneously to follow the leader or has some limited rotational speed. And we can look at transfer entropy across these, and we're basically checking to make sure that this does what we want it to do. And in fact, when we run this, we do see separation, at least over longer time periods. Over shorter time periods, and also note that the horizontal scales on these two axes are not the same. So this is your, these are your distributions that are giving us our estimate of the transfer entropy. And you can see the perfect follower, followed by a limited follower, followed by a limited follower following a different leader. The fact that this isn't 0 just has to do with the fact that when you limit how far a follower can jump on a circle, a lot of times you're going to hit the max. And so it's not as random. And so the two followers are likely to align with each other a certain amount of the time. And then two completely random leaders, you can see are down near 0 where they belong. When we don't measure for as long, we don't get as clear of results, but we start to see maybe some movement here. And again, like I said, the horizontal axes here are not the same, so this is pretty clustered near 0. So at least given enough time, we can detect leader-follower relationships in this simple example. I think something that's really interesting about transfer entropy here is that simpler scenarios are not always easier. We're very used to, in math or computing, would reduce the dimensionality of the problem, and that makes it easier. But because of the way transfer entropy has a subtraction term, if there's a lot of structure in the follower, a lot of inherent structure in the follower's behavior, which you tend to get more of in lower dimensional spaces, you actually, the problem becomes harder and the transfer entropy becomes lower because you can get pretty far just using the one signal by itself. So we're still working on this. This is actively in progress. Watch this space. And we're really thinking about how to calculate this faster and moving more towards real world signals. So taking a look at the time, I got very excited about my introductory slides. So I am going to actually skip a section talking about learning in the wild. Maybe we'll look at one video just for none of this. Not in the wild, not in simulation. There we go. We're going to look at one video because I know you're all here for robot videos. That's why they ask us roboticists to do talks, is because we have cool videos of robots. So here's a robot picking up a block and learning to pick up a block and put it in a bowl. And then it learns, won't show it in this video, but it learns to pick up the bowl and dump out the block, which is very convenient from a learning perspective because you get this nice, slightly randomized reset. So you can actually keep running this for a long time. It's a very nice, successful demonstration. We actually looked at different methods of having the robot actually model from a sensory perspective, whether it was succeeding or failing, and using people in the environment to help get labels. So what the robot does is, while it's interacting with these objects, it keeps track of what happens. It groups what happens according to, I think this is success, I think this is failure. And then as soon as it gets a real label, it can update its model and update, oh, okay, I think that actually is success. Oh, I think that actually is failure. And we looked at some different strategies for how to ask people about it. But when we actually go into the wild, you can see, you can get labels from people about half the time, or even a little bit less, depending on the specific task. And you'll notice that the errors are pretty brutal percentage here. 19.5% error conditions. That sounds about right to me. Hopefully anyone who's ever tried to put a robot into a public space with minimal supervision will sympathize with our pain here. But you can see that we did succeed some of the time, which is always nice, and that people gave us a mix of labels, maybe slightly more success labels than failure labels. So this is, failure means I failed a step of the task, success means I succeeded in a step of the task. And this is that result I was previewing earlier. This is the number of people interacting with the robot. The dotted horizontal line is the number of, is 1. And you will notice how very rarely that line is exactly at 1. And this interaction, because the robot kept moving, regardless of whether or not a person was there to give it feedback, and we actually got a lot more attention qualitatively than I've seen in other studies I've done in public spaces, which is another advantage, this kind of method that lets a robot learn even when there's not a person present. It actually helps you get more data from people because the robot's doing interesting things even when there's not someone there. It takes a certain kind of person to walk up to a robot that's standing perfectly still and go, what does it do? And you get way more people who will come up to a robot that seems to be doing something and is maybe asking questions. So recently, and here we'll pick up the talk again, I've been doing a lot of stuff with reinforcement learning. And there's a few reasons for this. One is it's a really fairly popular method in robotics for learning because you can define what success looks like. You tell the robot, okay, here's your success condition. You get a reward for it, 10 points. You score 10 points every time you get the block to the goal, every time the light goes on. You get 10 points and you get -1 point for every extra second that you take to solve the task. And so the robot takes some actions, it interacts with the environment, and it gets some rewards. In practice, this works pretty well for learning tasks, although like many machine learning methods, it tends to be a lot slower than we would want it to be. Certainly, it's much slower than a person learning a similar task. And so I'm interested in human-robot interaction. My question is always, what happens if we put a human here? We can put a user into this loop here of robot environment and have the user actually observe what the robot's doing and give some feedback. And the interesting thing here is that user feedback tends to be more dense than the reward function, which is, there's a little subtlety there in that you don't tend to get feedback on every single little thing you do from the person, but the reward function is often defined only at a goal state. So that's very sparse. You sort of wander in the wilderness until you happen to find success, and then you can optimize what you're doing. This is a sort of very informal description of how reinforcement learning often works in robotics. But a user can help point you in the right direction, but they tend to be a little bit more unreliable. You also don't always know if the user's feedback is going to align with the reward function. You certainly can't assume that it will always be the case. But there's evidence in this interactive reinforcement learning or interactive robot learning that incorporating a human's feedback in this way can actually help robots learn faster. In fact, a lot faster. And so my most recent work has been looking at different kinds of feedback, richer feedback in particular, looking at better user models, especially for early algorithm development, and looking at different kinds of actions and environments and that allow for this incorporation of user feedback onto new kinds of problems, in particular continuous actions, which comes up a lot in robotics. We like to, as computer scientists, we like to discretize. The real world has this unfortunate continuous property where discretization messes things up. And so we want to have continuous actions here, which requires adjusting some of the techniques and adjusting how we're actually incorporating feedback from the teacher. So I should have enough time to go through some of these recent projects. My student Jindan has been thinking about designing better oracles. So early algorithm development, we can't run a human subject study every time we want to change one little thing about the algorithm early on. At the end of the day, if an interactive reinforcement learning algorithm isn't shown working with people, nobody's going to believe it because, again, all the things that we know about humans, you can't perfectly simulate a human. If you could, you would have solved HRI already. And so you can't solve HRI to solve HRI. It just doesn't work. So instead, we use oracles. And these are usually pre-trained models on the exact same problem. And that's good in a lot of ways. That lets us say, in the best case scenario, would this even work at all? But it tends to leave, especially your early algorithm development, really vulnerable to common errors and issues with how humans give feedback. So some collaborative work I did in my postdoc was looked at the ways in which these algorithms assume that people are always paying attention to you. And so if you don't get feedback, or you get feedback that varies in reliability, you can't necessarily handle that. And so Jindan is working on trying to both understand how to design a more human-like oracle and to really incorporate users in this. And this is an idea that I think is really cool, which is the idea of user-centered algorithm design and involving users in algorithm design in ways that maybe you need to be an expert to design a new reinforcement learning algorithm, but you don't necessarily need to be an expert to think about how you might teach a robot. So what we do in this work is we replace the standard oracle with a modified oracle. And all that means is we take a pre-trained model, and now we're going to take whatever that model gives us, and we're actually going to modify it. And we're going to modify it across a few different attributes, including the frequency, how much delay there is, something we call motivation, which is whether it's reward focused. So it's basically if the robot did something right, how likely are you to give it positive feedback? If the robot did something wrong, how likely are you to give it negative feedback? And we can actually model these separately. And so a reinforcement learning algorithm would assume that if you do something right, you always get positive feedback. If you do something wrong, you always get negative feedback. But if you've ever been taught by a human, you know that some teachers like to encourage you when you do things right, and other teachers like to correct you when you do things wrong. And it's not always completely balanced between the two. We also look at bias, which is a potential shift in the feedback, and error, right? Humans are imperfect, and sometimes they will give you incorrect feedback. Error is the attribute that is most commonly currently incorporated into oracles. So they'll just say, assume a flat 20% error or 10% error, and we show that we're robust to that. But that, of course, is not actually, like, humans are not uniformly randomly wrong. And so we're taking a multifaceted approach to understanding teachers, including having people design a teaching persona, having them actually adjust the parameters of the algorithm, and then having them actually teach the robot. And what this is going to let us do is to look at both subjective and objective and quantitative and qualitative measures of what teachers are like, so that we can understand the relationship between how people see themselves as teachers and what actual feedback they give, how they model their feedback using the parameters that we've given them. And then we'll also interview them and find out, how they thought about what they were doing. And I think this will be, really has a lot of potential to change how we think about early algorithm development and try and make algorithms more robust. So I can see I'm running low on time, so we will maybe, as is traditional for all academics giving talks, I am low on time, so I will rush a little bit, but hopefully not so much you can't understand anything. My student Han Yu is thinking about rich feedback, specifically looking at scaled feedback. So most of the primary work here uses binary feedback. So you just get told good or bad. And you notice even in the previous project, we're really thinking in terms of you're told something is good or bad. And scaled feedback, which means asking people to score something, say on a scale of 1 to 10, doesn't really work as direct input to learning algorithms for the same reason you can't run a t-test on Likert scales, which hopefully that lands in this audience, which is that the math assumes that there's the same difference between a 4 and a 5 as between a 9 and a 10. And humans don't actually work like that. We also assume that a 7 means the same thing between different users. But one user, a 7 out of 10 from one teacher might be a 10 out of 10 from another teacher, or a 3 out of 10 from a third teacher. And even a single user can have their feedback change over time. But in this project, we think of scaled feedback not as direct input to an algorithm, but as a way to detect, again, looking for anomalies, changes, and being able to actually adapt to those changes. And so what this algorithm does, I will show the video here, is, oh, go away. There we go. What this algorithm actually does is it classifies feedback into 2 distributions, one for positive feedback, one for negative, and it tries to maintain separation between the distributions over time. And so this lets you notice outliers in your feedback, and it lets you know that, say, a positive that this particular teacher you should really only count a 10 as positive. Or for another teacher that even getting a 7 is good. So it lets you adapt to the teacher, and it lets you adapt to changes over time because these distributions can shift. So we did actually evaluate this on a lunar lander, which again, not quite a real world robotics task, but at the time we did this work, we weren't even allowed into the labs. And we showed that this was actually better across a bunch of different kinds of variation in the mean, standard deviation, and error probability of feedback using, of course, a perfect oracle that is modified to have these different kinds of error. We also showed that it had this good performance across 2 different underlying algorithms designed for binary feedback. And then, let's see, the title is "This is not updated." And then finally, my student Isaac has been looking at, as I mentioned, being able to do learning of continuous tasks, which come up in robotics all the time, incorporating user feedback while still having environmental reward. And so this is a soft actor critic based algorithm that uses the teacher to shape continuous action choices. So because it's continuous action choices, what we're getting out of these algorithms is not a discrete choice, but actually a mean and standard deviation over your action or actions. And we find that the teacher can improve early action choices. Having a teacher makes a big difference early in learning, and that seems to stabilize the environmental signal somewhat. We evaluated again in simulation, but at least this time we have a simulated robot, so that's a little better. And we had to simulate human feedback with some heuristics that were not aligned with the reward function, but not generated from the reward function. So for Bipedal Walker, which is this little creature that has to learn how to walk, We used a heuristic of perceptible forward motion, so forward motion that was larger than a threshold. And for the robot push task, we used a heuristic of pushing the ball at all, which is a pretty straightforward heuristic for a person even to define of like, this is a pretty good start on your learning task is like, did you touch the ball and did it move? And we showed that that we outperform prior algorithms for learning from human feedback unless they receive perfect feedback on every single frame, which is this superhuman gray line you see on the rightmost graph. And that we substantially speed up learning, especially early in training. And on the robot push environment, we outperform even this parallelized algorithm with 6 agents learning simultaneously. Having one human who knows what they're doing is a lot more beneficial than having 6 agents that are just randomly doing things. And so we've been working on, Isaac has been working on now learning models that looking at different kinds of models that give users more control over parameters. And this is inspired a little bit by Bipedal Walker and wanting to control the walking speed, which seems like a really obvious, easy thing you would want to be able to do, but out of the box, learning algorithms designed to do this will completely fail if you suddenly set a maximum threshold on how much the motors are allowed to move. Because the policy was trained under one set of assumptions and you change it and all of a sudden everything falls apart. So we're looking at ways to do this more effectively than just doing domain randomization. But that work is very, very early stages. All right, so wrapping up, not too late, only 5 minutes over. And we started a little late, so it's fine. I'm really interested in these sort of 3 areas of robust learning for robots, particularly robust learning with the assistance of human teachers. Looking at these continuous actions, rich feedback, better oracles, incorporating more of a human touch to the robot learning. I'm interested in getting robots into the real world. None of my recent work has been on robots in groups or in public space learning, which was my previous area of specialization, because this has not been a great time for doing that. My hope is in the next year or 2 to be able to get back to that. But we have been looking at attention modeling, which we can do through our new lab's big picture window, which should help with social distancing while still doing human-robot interaction. I also didn't talk a lot about assistive robotics. We have a new, brand new project funded by the National Robotics Initiative that's going to be looking at mutually assistive human-robot interaction. So being able to think about, instead of just robots helping people with disabilities, actually thinking about people with disabilities and robots helping each other, and really putting the robot in its true place as being occasionally kind of terrible, and humans as being pretty good at doing a lot of things, even disabled people, which is sometimes not adequately represented in the research community. I also do a lot of disability advocacy. So I will throw up my disability advocacy slide here. I have a disability, and so I am very involved in the self-advocacy community. I am actually new co-PI of Access Computing, which works to increase the participation of disabled people in computing careers. I think my official role is something like liaison to the HRI and robotics community. My hope is to get the robotics community thinking about accessibility as much as the HCI community has been. I'm also a member of Access BostonCHI, which is an organization that works to improve the accessibility of CHI conferences, of which HRI is one. I don't necessarily need to remind you all of that, but sometimes the HRI community needs to be reminded that they are a CHI conference at least half the time. And I also advocate for accessibility in SIG-CHI and in the ACM at large. I have a side project messing around with PDF accessibility. If you are a PDF expert and would like to make my life easier, definitely send me an email. I would love to talk to you and pick your brain about this. All of the current tools for remediating PDFs for accessibility are very UI based and involve a lot of doing things by hand that I, as a computer scientist, find abhorrent because I think we should be able to automate these kinds of things. So I have been working on that. I developed some teaching materials for teaching about disability and accessibility in HRI classes. They're actually on our website. I'm happy to share them. I'm happy to talk about how I developed them. And if you want to learn more about teaching accessibility, definitely send me an email and I will put you in touch with the people at Access Computing who are really expert in that. I'm a member of the organizing committee of TAPIA. I was the scholarships chair. Unclear what I'm going to be doing next year, but I am on the hook to help out again. And I also host RU students through the DREW program. Hopefully everyone here who has contact with undergrads is familiar with the DREW program. If you're not, it's a distributed research experience, which means that undergrads from historically marginalized groups can apply and get matched with a research advisor for the summer, and they actually go and do research. It's a really fabulous program, and the students are great. If you are an academic and you are not already a DREW advisor, I strongly recommend applying because the students have really been almost uniformly excellent. Some of my best students. So with that, I'm on my last slide. Thank you for having me. This work was funded by the National Science Foundation, and some of the earlier work was partially funded by the Office of Naval Research. If you want to help me out in my research, encourage students to apply to Tufts for a PhD or master's degree. We actually have a human-robot interaction program. As far as I know, it's still the only one in the country, and it's pretty fabulous, in my completely unbiased opinion. I am also looking for a postdoc for this project on mutually assistive robotics, especially someone with experience in assistive technology or with a strong interest in assistive technology. So definitely, if you are looking for a postdoc or you know someone who is, send them my way. You can visit our lab website, and we also have a lab Instagram because I don't do Twitter, but we needed some place to put robot videos. And of course, thank you to my wonderful students. You can see I have included their pictures without masks. Actually, it's in a different order, which might be a little confusing. So you can see what they look like. But they have done a really fabulous job in an extremely difficult time to be an HRI researcher. And with that, I think we can move on to questions.
All right. Thank you so much, Elaine. This has been fascinating. I have like 1,000 half-formed questions, but I'll open it up to other people first. Any questions? You can raise your hand and then just ask it. Annie has a question. Annie, do you want to ask your question?
Yeah, I was just trying to clarify your request regarding the PDFs.
If you are an expert in PDFs or interested in becoming an expert in PDFs and would like to help out with automating tools for making PDFs accessible, particularly making academic papers accessible, that's a side project that I'm working on that I could definitely use help with.
Thank you.
All right, other questions?
I have one question.
Go ahead.
So, I mean, I've noticed in your studies, your robots have like different levels of anthropomorphic properties. So I'm just trying to understand what's your process of choosing which kind of robot will be used for what kind of study?
In general, by default, I like to use this kind of robot. So it's got a face, it's got a head, it's got pan tilt, but it's not a super hyper realistic face. The face is pretty forgiving of not animating it, which is the biggest problem with having a hyper realistic face. If you have a realistic face and it doesn't move, it looks weird. If you have a little emoji face and it doesn't move, it's kind of okay. It's enough to give people kind of those like warm fuzzy feelings of like, this is an agent, but it doesn't set a lot of really high expectations. So that's kind of like that's like the starting point. And then going up or down from there, So for the tabletop robots, they actually are similar in a lot of ways. They have different degrees of freedom in the body, but they actually also have animated 2D faces, relatively similar degrees of freedom in the face to this like LED screen. When we do stuff with just the arm, that's typically when we're doing something that's more robotics focused and not HRI focused, potentially even things that don't have a human, if it's just robot learning. Sometimes we'll pull the arm off and use the arm separately. Again, it tends to be, for example, if we have a setup where the position of the arm is really important. We actually jokingly call the robot where the arm is clamped to the table, we call that table bot. It's a table with an arm. Yeah, so that's sort of generally how we think about the thought process. If I were doing some like really intensive social stuff, like if I were doing gaze, or maybe like I don't know, I really wanted subtle emotional expression, I might have to have a different robot from these even. But I tend to use social interaction. Social interaction to me is a way of making robots that work well with people. I don't so much study that on its own. And if I did, I would probably just have different robots in my lab. If you're thinking of designing your own robot, 2D LED panel face plus arm is like the way to go. Don't try and do a hyper realistic face. It ends up, that's how you get the uncanny valley.
So thinking about that robot you had, and the person who was like talking to that other guy standing in front of the robot, like what I'm wondering is like how important is it for you, like as a robot algorithm designer, to think about like all the intricacies of human behavior and mannerisms and how we socialize? Like, is that important, or does the robot kind of learn on its own and figure out like, oh, that's not an important cue?
It depends on exactly what we're doing. If there's one thing I can tell you about HRI is that the humans will meet the robot way more than halfway. And that often the thing that people care about more than anything else is whether or not the robot works. So one of my lab mates from grad school, Ross Mead, did a really interesting paper where he was looking at proxemics. But there's a bunch of research on HRI on how far away should the robot position itself from the person. Should it be 3.5 feet or 2.5 feet or 4 feet? And then he did this great study where he looked at, okay, well, what if we vary how well the robot works at different distances, and then ask people where they want the robot to be? Turns out people want the robot to be wherever it works the best. So to me, I think the main driver is in, is like how well the robot works. And so understanding how people think and how people do, how people socialize, how they attribute what the robot's thinking and how that affects what kind of feedback they give the robot. These days, that's mostly how I'm thinking about social interaction in the context of robots. But I am, sort of in the big picture, long-term, very interested in social rules as they pertain to like social appropriateness. So making sure that while the robot's trying to do something, that it's not basically being a huge jerk and annoying people. So I sometimes like the goal is to build a robot that is not annoying. And most current robots don't really pass that test.
Thank you. James has a question.
Okay. All right. Sorry about that. Hi. Great talk. I had a quick question for you, which is, so in the feedback condition, let's say, so if you have the robot doing something in a mall and someone comes along and, says, oh, that was no good, what you just did. I'm wondering, is there some way, like, if someone has already given you a bit of input, then that they're probably willing to give feedback. Like, I wonder almost if the robot pulled up a screen and said, hey, this is how I did it earlier. Was that good? Yes, no. Was this good? Like, could it kind of it would be annoying for the human in some sense, but like it would be amazing how much more information you could get. Because usually, if, like you said, if someone's willing to give a bit of feedback, they're sort of already engaged and halfway there. And could you certainly sort of stretch it out and not force the robot to actually do the behavior again, which would take a while? Like I think people would probably be okay to watch just a fast video of ball dumps and things like that.
Yeah, so I think that would be interesting to look at. I can tell you, you will lose people a lot faster if the robot doesn't move. Like the number one thing that made people go away from the robot, which I didn't have time to talk about on that graph, but you see when the robot messes up and starts over, people leave. When the robot, people really want to see the robot do something cool. And
Yeah,
so
novel.
I think if you brought up a screen, if you like made the robot move, you're like, before I move again, would you just look at this one quick thing? Then you might be able to get people, you get kind of like one bonus feedback
Right.
per question. But I think at the end of the day, unless you could really get someone to sit down and like, okay, you're here. Would you like to give me 15 minutes of your time? Which like basically no one does, especially students, right? They'll give you 3 to 5 minutes, except for there's like maybe 1 out of 100. We had one person who stayed for half an hour in that study, which was a lot. But 1% out of 100 will be like fascinated with the robot and just wants to be there all the time. But most people give you 5 minutes or even less, 3 minutes. The amount of additional feedback you're going to get is not that large. Like it doesn't solve a lot of the problems of you have to get feedback from a lot of different people. And it's going to be, I could show video and speed it up by like, twice as fast, but I'm still only getting 3 pieces of feedback per feedback. I'm not getting 1,000, right? I'm not running this through, I'm not training an end-to-end deep neural net on this amount of data. So I have to think about how I pre-train parts of the network or, refine how I'm representing the space so that I can learn. So I think it sort of doesn't fundamentally change a lot of the problems, but it is certainly a way. We've been thinking about ways that we can get people to like walk by the lab. If someone were at Tufts and happened to walk by the lab and wanted to spend half an hour giving our robot feedback, if you're volunteering for that, then, we've been thinking about how to get people who are walking by the lab to give us a few pieces of feedback. And videos are good, although if you can get a real robot to move, I can probably get a person to stay for twice as long if I have the robot move than if I'm showing videos of the robot moving. And so you sort of get, I think the net amount of feedback you get is probably similar.
That makes sense. Cool.
So I'm wondering if maybe you could elicit more feedback from humans to the robot by, this might be down the road a little bit, by injecting some humor. For example, you had the student and his advisor standing in front of the robot talking, no doubt about the robot. Perhaps one day the robot will be able to say, I hear you talking about me and I'm right here in front of you.
So this isn't exactly humor, but similar to what you're talking about. There's a really excellent paper from Sean Andrist at Microsoft Research where the robot asks people if they're messing with it. So it's a direction giving robot. And the study is basically when people come up to the robot will say like, do you actually need directions or are you just messing with me? And it freaks people out. They'll like be like, I definitely needed directions to here. And like so all of a sudden it like totally changes the interaction. So I think robots doing humor on purpose, except in the sense that like roboticists have a sense of humor and will sometimes program that into like a hard-coded behavior, but robots being clever, I think we're still a long way away. I think generally the problem of engaging people and designing kind of like engaging fun interactions, definitely look at the Disney robots. They're amazing at that. We do some of that, but the odds of it landing flat are very high, and the odds of it freaking people out are also very high. People don't like it when the robot is too different from their expectations, which is one of the reasons, again, talking about the appearance of the robot. We want that appearance of the robot matches the behavior of the robot, matches people's expectations. Everybody feels relaxed and happy. One of those things is off, and some people won't care, but definitely some people will be very creeped out by your robot.
Mhm. Thank you.
Other
Could I ask one more
questions?
question?
Go ahead.
If that's okay, I'll
Yeah,
just
sure.
jump in for one more, if that's okay, Elaine. So yeah, recently I started giving my Alexa feedback, and I realized she took it. Like when I said, Alexa, that was totally wrong, she said, thanks for the feedback. And I sure hope that they are actually incorporating that, and Alexa should be getting smarter and better. But my sense is that's a false hope. And I think part of the problem is that sort of the Alexa gods haven't told people or encouraged people to give the feedback to the robots. Do you know, are they doing much with that? Do you know much about what they're up to in that space, like for conversational agents and eliciting and using feedback?
Yeah, I don't do a lot with language. That's partly because Matthias does a lot of language stuff. So at Tufts, there's another professor who does a lot of stuff with language and robots. And so it behooves me to have my own thing. But it's actually also just me personally. Natural language processing is awesome, cool area of computer science research that I never wanted to do because I'm a roboticist and I want to do robots and I care about things that move. So I don't do a ton of stuff with the conversational agents. That is, I will say though, that when you have something that is on the scale of the Amazon agent or the Apple agent whose name I can't say, or to wake up every device in my house, then you're just playing a completely different game with data, right? One person's feedback is essentially irrelevant unless you're doing something on board. And as far as I know, they're really not at the point of doing that kind of like onboard adjusting. It would be very cool if they did it so that, you know, your Amazon friend would know that you particularly have an opinion, right? Similar to what they do with music, right? Where you give a thumbs up, thumbs down. But I don't know that they're doing a lot of that yet. It's about the same as putting in an error report. If you're lucky, a lot of other people put in the same error report and then it might get some attention.
All right. Any last questions before we call it a night? All right. Well, in that case, thanks so much, Elaine. This has been fascinating. Really, really enjoyable.
My pleasure. Thank you for having me.
All right. Well, good night, everybody, and see y'all in January at the Jared School event.